In this episode, we'll look at repetition codes to mitigate the effect of a noisy channel. So repetition code is simply an encoding where you use a block of symbols to represent the symbol that you want to transmit. So in the example we'll be carrying through, we will take a 0 and encode it as 3 zeros, and then take a 1 and encode it as 3 ones. So the string 011 will get encoded into 3 zeros, 3 ones, followed by 3 ones. So it's a simple code. In decoding, we want to find the optimal choice for being 0 or 1, and by that I mean the choice that has the least probability of introducing an error. So it's a probabilistic problem. We receive 3 symbols, S1 through to S3, and then we want to choose our value for x, given that we've seen symbols S1 through to S3, and want to choose the value such that it's got the highest probability. Using Bayes' rule, we can invert the probability of x given the symbols we've seen into the probability of x, the probability that given x is a particular value that we would get those symbols, divided by the probability of the symbols or the evidence. And since this is a binary choice, we want to compare effectively two models, the model where x equals 0 versus the model where x equals 1. And so this is really a model selection problem, and we could use the odds ratio. So that is the posterior probability of x being 1 given what we've seen, divided by the posterior probability of x being 0 given what we've seen. Now let's assume we know the structure of the channel that we're sending the symbols through. And to be concrete, we'll assume it's a memoryless binary symmetric channel, so that the symbols, the probabilities of the symbols going into the channel is probability A for a 0, 1 minus A for a 1. Then the channel with a probability 1 minus F will transmit the symbols without error, and with a probability F will flip the symbols. So it's 1 to a 0 and a 0 to a 1. So with this encoding, we already have the probabilities for x being 0 and x being 1, some of the ingredients we needed for the odds ratio. The other major piece we need is the probability of the symbols given the value of the input. Since this is a memoryless channel, the probabilities of each symbol are independent, and so we can just count the number of ones we see. And so, for example, the probability that given that x is equal to 0, that we see n ones in this string will be the probability that n ones got flipped with probability f, since it started off all in zeros, and 3 minus n with probability 1 minus f that didn't get flipped. Conversely, if x equals 1, the probability that we see n ones is going to be n of them must not have flipped times 3 minus n have flipped. So now the odds ratio looks like this. We can use Bayes' theorem to expand the numerator, and you'll have the probability of x and the probability of the symbols given x divided by the probability of the symbols, and expanding the denominator, we'll have the probability of x, the probability of the symbols given x, times the probability of the symbols, so that evidence term will cancel. And then substituting in the values we've just calculated, we'll have the probability of x being 0, the probability of x being 1, and the corresponding likelihoods. Then simplifying, we end up with the expression at the bottom. Since this is now a function of a, which ranges between 0 and 1, and f, which ranges between 0 and 1, we can plot it in a 3D graph, and it looks like this. So this is the case for when we receive 3 zeros. And what I have plotted here is a is along this axis, f is along this axis, and along the vertical axis is the logarithm of r. So a large negative value of the logarithm of r favors interpreting the symbol as 0. A large positive value favors interpreting the symbol as 1. An f of 0 is when we have no errors, so there's no probability of a bit flip, and this is an errorless channel. And f of 1 is also an errorless channel because we've flipped every single symbol and we can simply decode it. Along this axis, if A is 0, this is equivalent to the source only sending 1s because A is the probability of sending a 0. And if A is 1, the source is only sending 0s. So here are the 4 possibilities that could show up. So we could have no 1s in the symbols that we see. We could have a single 1 somewhere. We could have 2 1s, or we could have all 1s. And you can see that the case of all 0s or all 1s are kind of converse of each other, as is the case of 2 0s or 2 1s. So what Bayesian inference is telling us in this case is basically to use a majority vote to decide the bit. And the modifications to this majority vote is to adjust for what we know about the input distribution and the channel structure. Now, if the probability of sending a 1 or a 0 into the channel is approximately a half, and if the probability of a bit flip is small, this basically becomes a majority vote. So for A equals a half, we're sitting along midway along these directions. And for f equals small, we're sitting down this end of the graph. So you can see if you see no 1s, it would suggest you should interpret the symbol as 0. If you only see a single 1, again, you should interpret it as a 0. If you see 2 1s, you should interpret it as a 1. And if you see all 3 1s, you should definitely interpret it as a 1. Now let's look at the effective error probability once we've encoded. And for simplicity, we'll assume we're working in this case where A is approximately a half and F is small, so that the majority vote decoding is the optimal choice. And the question is, what is the effective error probability and the rate for the communication for this tripled code? Since we're decoding by majority vote, a case where an error would not be detected and would get through the decoding would be if we had 2-bit flips. So imagine we were sending 3 0s, then if the first 2 or the first or the last 2 both get bit flipped, majority vote would then interpret each of these cases to be a 1, which would be incorrect. And this occurs 3 times. Or you could have all 3 of the bits being flipped to a 1, and then again we would interpret this as a 1. There are 3 lots of 2-bit flips, and 1 bit is not flipped, and 1 lot of all 3 bits are flipped. Simplifying gives you this expression. The rate of the code is simply a third, because we're transmitting 3 symbols in order to send 1 encoded symbol. Now let's go further. What if we didn't use a 3 code, we used a 4 code or a 5 code or a 6 code? Do we get an advantage in this? Well, the first thing to realize is that the number that you use in the code can't be even, or we could get an undecided result. So we should use an odd number, so 3 or a 5 or a 7. And then we will get an error if more than half the bits are flipped. In other words, if n plus 1 upon 2 or higher bits are flipped, we would decode this as a 1 when we should have encoded it as a 0, for instance. We can calculate the probability of this event. So we're going to sum up all the cases from n plus 1 upon 2 up until n. And for each of those cases, we have to have j symbols being flipped and n minus j symbols remaining unchanged. And then we count up all the cases where that can occur, which will happen n choose j times. So in the case where n equals 3, it reduces down to this expression, and we'll have 3 choose 2 times 2 bits are flipped, and 3 choose 3 times where all 3 bits are flipped, which leads to the expression that we had earlier. Now to simplify it further, rather than take the entire sum, let's take the leading term. Now the leading term in the sum would occur either when this prefactor is large, or since f is small, when j is small. And because this is the binomial expansion, this happens to coincide at j equals n plus 1 upon 2. So the leading term will be choose n plus 1 upon 2, and then we flip n plus 1 upon 2 of the symbols and leave the rest alone. And the rate is simply 1 upon n, since we're taking n transmitted symbols to send one encoded symbol. So let's take the probability of a flip to be 10%, so 0.1. Then if we were to use a single symbol, then our error rate would be 10%, and our rate of communication would be 1. By using an encoding across 3 symbols, our rate now drops to a third, and our error rate is just going to be that leading term in the expansion, which works out to be 0.028, which is somewhere around there. If we were to go to 5 symbols, again our rate would drop to a fifth, but our error rate would also drop, and so on. And so we can reduce the effective error rate that our communication sees through this noisy channel, but at the expense of using longer and longer codes. And so we're communicating at a rate that's slowing down. Let's look at a final example that kind of illustrates the point. So here is the source, which is an image from XKCD. And it's an algorithm for calculating a guaranteed random number. I've purposely pixelated the image so it'll be heavily affected by noise. Now, as far as we're concerned, this is just a bunch of ones and zeros. 0 to denote the blank white space, and 1 to denote the black pixels. And if you count in this particular image, it turns out there are somewhere of the order of 55,000 white characters or white pixels, 55,000 zeros, and there will be 3,000 black pixels or 3,000 ones. And so the probability of seeing a 0 from the source is going to be 0.95. Now we pass it through a noisy channel, and in this particular case, the probability of a bit flip is going to be 0.15, and this is the message we see. And possibly if you squint at this for long enough, you can kind of make out some of the words, but it's pretty hard to really be sure unless you happen to know what the message was. Now let's introduce a redundancy encoding. The one we've been talking about, we encode a 0 into 3 zeros and a 1 into 3 ones. After decoding with this is the result. And now you can actually make it out what the original message was. There might be some contention about whether this is a 4 or a 9, but then you can kind of make out what it says in the comments. Chosen by a fair dice roll, guaranteed to be random. Okay, so we're talking about a dice, so it's between 1 and 6, so this should be a 4. And pretty much every other character you can make out. Now what happened here was we look at the odds ratio, or rather the logarithm of the odds ratio for receiving a certain number of ones in the output. And we find that if we see no ones, it strongly favors decoding as a 0. Same if we see 1. Same as if we see 2. It's only the case of 3 ones that decodes as being a 1. And this is because we know that the source is mostly sending zeros. So we'd have to see an exceptional event to be able to decode a 1. In terms of the graph that we saw before, we're sitting along the intersection of these two lines. This first line is A equals 0.95, and this line is F equals 0.15. So it's here somewhere. So if we see 3 zeros or no ones, we decode it as a 0. If we see a single one, we decode it as a 0. See 2 ones, we still decode it as a 0, and it's only the case of 3 ones that we decode as a 1. Now digging a little deeper, it becomes intuitively obvious why this is all working. So if we look at the encoded message, it looks like this. So I've replaced every single black pixel with 3 black pixels. So it's like I've bold fonted the message. And then when you add random noise, you tend to still see the letters because they tend to cluster together, whereas the random noise does not. And so we've encoded our message in a way that is robust against the noise. Now, of course, we didn't actually have to do this. If we're transmitting a picture, if I hadn't sort of pixelated so badly initially, we would naturally get this kind of thicker lines, and then there's a correlation between nearby pixels. And this is really not a string of ones and zeros, but this is a message that lives in a 2D plane and has got a certain structure, so that if you have a certain black pixel somewhere here, you expect the nearby pixels to also be black with a certain probability. And we've taken none of this into account in our encoding. And so if we throw in a more sort of stronger font message into the noise, then because the noise does not cluster, you can still see what the font was. Now, of course, you should appreciate that we can always adapt our encoding and decoding procedures to take into account what we know about the message and these spatial correlations, and that can all be done within the Bayesian model that's doing the decoding.